strong indication that there might be autocorrelation in the time series. We discussed last week that heteroscedasticity is something which is relevant in time series analysis, in the time series context. Then we deal usually with arch models or gauge models. These are discussed next semester in the time series analysis course. Heteroscedasticity is also relevant in a cross-sectional thing, and maybe particular in the cross-section. We discussed last week this example of income, of the relation between income and food expenditure, right? And that there is, of course, for rich people much more variation and much more uncertainty than for poor people who more or less spend all each month the same amount, more or less everything for food. Okay, so for cross-section, definitely important. Also, in many applications for time series analysis, the way you deal with it is probably different. So autocorrelation, however, is something which actually makes no sense in a cross-section application, right? Because it is about, you obviously know, look, we talk about the correlation of UI, U100 with U99 or so, right? So if it's just a cross-section, so if I is just the number of the person, the number of the individual, right, then obviously the ordering is totally arbitrary, right? It makes no sense to say, number 100 has a correlation with number 99, and 99 has some correlation with 98 or something like that, right? That makes no sense. So it's just arbitrary, right? It would not be arbitrary, of course, if there is somehow a natural ordering, right? So if I know the ordering of you here, and if we write now an exam, and I see the errors, of person X are closely related to the person who sits right beside him, right? This information, right? This is kind of autocorrelation then, right? That the exam for people who are close together are somehow similar. That would be a sign, right? That some autocorrelation is going on, right? But usually, the natural application of autocorrelation is in a time series context, where you have where there's an obvious natural ordering of the observations, and it makes really sense to talk about, well, how does yesterday depend on today, and today on tomorrow, and so on. All right. So, these are the two cases we talk about now, and before we do so, we discussed, well, suppose we just don't care, or we just don't know that there is autocorrelation of our heteroscedasticity. That is, we don't know that the covariance matrix of the errors is not diagonal, but some positive definite symmetric matrix omega, right? But we ignore it. Okay? Well, it might happen. Yeah. Then we apply to a model with this omega covariance matrix, just the ordinary least square matrix, and now we start to emphasize when we use the ordinary least square estimator, because now we're going to talk about generalizations of that ordinary least square estimate. So what we did so far, the least square estimator is the ordinary least square estimator. We can still show that this estimator remains unbiased under the same assumptions here, where we showed that it's unbiased, simply because if you go to the proof, the only assumptions you need is that the errors have expected value 0, and that exogenate assumption. Right? If you go to the proof, it's one-liner, there is no omega, there is no covariance matrix, it doesn't play a role, right? And that's the beauty of these mathematical proofs, right? It does not only show you a result, it's also, if you look at the proof of that proposition, you also can see which assumption do I actually need to prove this, right? And the covariance matrix doesn't show up. All right, therefore, it remains unbiased, even if there is some general omega, as long as the axis exogenous. All right, But now let us look at the covariance matrix, right? So this more or less says, well, you know, estimating is more or less okay. It is, however, not better than okay, right? Because, again, if you look into the proof of the Gauss-Markov theorem, you see that we need the assumption that the covariance matrix is sigma squared times identity matrix, right? If that doesn't hold, then you can't finish the proof, okay? So no surprise. If we apply the ordinary square estimator to a model where the covariance matrix is not diagonal, so if there is some heteroscedasticity or autocorrelation, then the estimator remains unbiased, all right, but it's no longer efficient. All right, that's clear. That's the estimation, the point estimation, so to say. Yeah, but what about the covariance matrix? And here in the derivation, I think it's also on the exercise sheet. So this is the derivation of the covariance matrix of theta hat, right? And the only thing here is, you know, this is just a matrix diagram, right? So to derive this, and the point is, well, if omega would be sigma squared times identity matrix, so if we were back to the classical assumption, then here sigma squared times x prime x minus 1 blah 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 would result, right? But in the general case, you see, well, in this here is not diagonal or just a multiple of the identity matrix. Then the covariance matrix looks like this, and this is obviously very different from the covariance matrix we would apply if we wrongly assume that omega would be sigma squared times identity. So in other words, this equation here shows you that if you apply ordinary least squares to a model where the residuals are either autocorrelated or heteroscedastic, then the standard errors you use are wrong. They are no longer valid. So the standard errors of the estimates, these are here the square root of the elements, right? But if this matrix here is just wrong, so this is the correct one, and it doesn't coincide with the naive one, with the ordinary square one, then obviously all the T and F tests and all the other tests, you know, which are more or less based on the standard errors of your estimates are just invalid. Okay? And you see, although we talk here about variances, kind of second order thing, this is a first order problem. Right? Because whatever estimation you do, people will ask you about estimation uncertainty, about a measure of estimation uncertainty. Right? They want to have tests. They want to know, is this really statistically significant what you say? Is this really different from 1, 0, whatever is relevant in your application? Okay, so testing, being able to make tests is obviously an important thing. Right? It's not enough to say, come on, I have a consistent estimate and it should be somehow close to the true value. That's not enough in practice, in academic practice. All right, so in other words, here you see the least square estimator is, if we are naive, it's still more or less okay, right? In particular, it's also consistent. Again, you can just look at the proof and you see that this everything is fine here, but the variance is based on wrong assumptions and therefore not valid. So there is something we have, there is action required, right? If we know, or if we see, or if someone thinks that our residuals are heteroscedastic or autocorrelated, then there's action required. Okay. So, and here are the two strategies which are common or possible. The first one, and this is the one we discussed last week already, is a GLS strategy. So the very brilliant trick is you have a model with strange covariance matrix omega, or relation, transform the model such that the transformed model follows again the standard assumption of the classical model. right? So make the residuals homoscedastic and free of autocorrelation by your transformation, and then just apply d-squared, right? That's the idea of deriving the generalized d-squared estimator. This is what we done. This is what we did last week already. And the second strategy, this is what we talked today about also, is, well, you know what, if you do this, right, obviously, you know, we derive it on the assumption we know omega. Of course, nobody knows omega. You may be able to test and to estimate omega, but still, you know, as we will see, all of this requires assumption, right? And whenever we do, we make assumptions. The question is, well, how valid are these assumptions? How plausible, you know, is this compatible with the data? So, you know, maybe, you know, if you can do that, if you have a good estimate for omega, then you can apply GNS. But if your assumptions about omega are just wrong, then your result is wrong. Then GNS is wrong, right? Obviously. Well, so is there some way to circumvent the problem with wrong standard errors without making concrete assumptions about omega? Yes. And these are the so-called robust standard errors. There are two kinds that are particularly popular in academic practice, and we talk about this. So this is just, you know, we say, come on, yeah, if we would know omega, then we could really have, again, an efficient estimate and perfect standard errors. Yeah, first best solution, right? But if we're skeptical or not interested in doing all the efforts to estimate omega, then that is also a very, you know, plausible idea to say, oh, come on, hey, I have so many observations, I know it's unbiased, it's a consistent estimator, so the estimation is okay, and I have here standard errors, which are robust to heteroscedasticity or articulation, so any critic should silence, because standard errors are okay. All right? So these are the two strategies which are applied. This is a slide that derives the GNS estimator, and you see, we just here, the important thing here is, we assume we know omega. Right? So first step, we assume we know omega. Okay, and then we know omega inverse, and this was just linear algebra, right? The things with the Cholesky decomposition and the eigenvalues, Leah discussed that in the tutorial nicely. So if you have omega, you can derive the psi, the phi matrix here, and here you see the trick. That's the brilliant trick. You pre-multiply your model with this phi matrix here, which is based on the eigenvectors and eigenvalues of omega. And you can easily show that the covariance matrix of these tilde U's, of these transformed U's, are now just second matrix. Right? That's brilliant, I think. Okay, so if you just, so in other words, all the classical assumptions we require for efficiency of ordinary least squares are valid, hold in this transformed model. So, okay, the beta is obviously the same. We transform only the variables. So let's run an ordinary least square regression of the tildes, and this is an efficient estimate with valid standard errors. Everything is fine. Okay, we really solve all the problems by this transformation. Yeah, okay, in order to have this phi, we have to know omega. Yeah? All right. So if you just apply ordinary least square to the tilde model and plug in what x tilde and u tilde and all these tildes here mean here by here the definition, if you just plug it in, this is the formula for the GNF estimator. This is one of the few formulas I would say you should remember. It's not a vocabulary test in the exam. They're asking you vocabulary. So what is the formula of the GNS? But if you can't remember that, if you see it, if you can't remember, then that's fine. You have not thought a lot about GNS. Okay. Again, just to make things a little bit more transparent. Look. 0, and on the diagonal everything is constant. So we are back to the classical assumption. Then omega is the identity matrix, and then you see everything cancels out here. Minus 1 minus 1 is omega. Omega times this is, then we're back to the least square estimator. So this is, in fact, here a generalization, so that G is here well reserved, a generalization of the ordinary square estimator. Okay. What you can also do then is just, applying the same variance, covariance, matrix algebra here as what we did here in order to write this formula. We can then easily show that the covariance matrix of your GLS estimator here is like this. So it of course depends on omega, right? And again, if omega is the identity matrix, you're back to the case of the ordinary square covariance. All right, so far, so good. Questions? So this is how I find that. Here, I think this slide I also presented last week already. Coming back to that, very similar example, slide later, right? But here is, so to say, on a bachelor level, right, with simple linear regression models and no matrices, right? An example how to transform a linear model with heteroscedastic errors, right? Here you see it's a linear model, everything's nice. But the errors here are not constant, the variance of the errors are not constant, but depend on some variable VI. Classical, like income through expenditure example. That would be maybe income. So the higher the income, the higher the variance or so. Right? And here you see how easy it is here in that example to transform the model such that the transformed arrows just follow the classical assumption of the linear regression model so that you can apply OLS to the transformed model. Right? Here it starts and applies before the transformed model where the two is. Okay? So if you do that, you see that it's nice because now you see that applying GNS in that example here means you apply a weighted least square estimator, because as you see here, this is minimizing the square of the multiplied model, and this is just exactly what that means here in that example. This, and here you see that the errors here, the deviations from your regression line, they are not treated the same. This would be the classical model. Each observation has the same information content. Each UI has the same variance, right? Here it's different. Here some eyes has high variance, not so reliable. Some eyes have small variance, more reliable, higher information content. And of course, the idea here is, well, if the information content / variance of an observation differs, if there is some which higher information content and some with lower information content, then it obviously improves the estimation if I take this into account, right? If I weigh those observations down with high uncertainty and weigh those up, is that right? Weigh up, right? I put a higher weight on those observations with a lower variance. And this is exactly what's done here. Okay. So the generalizing square looks here a little bit, what's going on, but it's very straightforward. It's very intuitive, the idea. Particularly in case of heteroscedastic regressions. Okay, so GLS can be interpreted as weighted least square. And here's a summary of the results. Here we derived for known omega, here the GLS estimator is obviously unbiased, it's consistent up to the norm. So yeah, well, these are all the properties of the ordinary least square estimator under the classical assumption. right? So not surprisingly, we got all the proofs here for the GLS works through the proof of the Gauss-Markov and everything here, consistency for the ordinary square, right? Because GLS means I can form the model in a way such that it's practically OLS. Okay, so that's not surprising, right? That GLS, if you know omega, is perfect. All right, but damn, don't know omega, right? So we have to somehow estimate it, right? If you apply, this is, maybe you find in some textbooks feasible GLS, and this feasible GLS means you do not just assume you know omega and apply GLS, but you look at the data and estimate omega somehow. Yeah, and that, of course, this is feasible in the sense that you know extra knowledge about omega, exhaustively coming from heaven or whatever, right? So, and this is called feasible GLS or SGLS, right? So don't be confused. What is that feasible? The GLS just means I estimate my omega from the data. So, in fact, yeah, you see, this is the empirically relevant case now we're talking about. Okay, so for the moment, before we talk about how to estimate omega, let's suppose we have an estimate omega hat, right? And we just replace the unknown omega here by its estimate. That's all we did, right? This is the feasible GLS estimator. We just replace omega by estimate. Well, and then, and this is, I don't know whether that's very helpful here, but it shows that if you, here we replace, so to say, omega by omega hat, or vice versa, this here is to show that if we replace omega by a consistent estimate, right? So of course, if that estimate is stupid, then it doesn't help a lot, right? Then of course the estimate that results from that is also stupid, right? But if it's a good estimate, consistent estimate in particular, then consistency of the GLS estimator, we already proved, for known omega, translate into consistency of the feasible GLS estimator. Okay, and all the other results also. Right? So if we have a good estimate for omega, if we have a consistent estimate of omega, then all the good things we proved more or less for GLS translates into feasible GLS. Right? Okay. But now, of course, well, first we started with, let's assume we know omega. Okay, maybe not so realistic. One step more to reality, let's assume we have a very good estimate for omega. Okay, then everything's fine. Next step is how to get this estimate, right? How to estimate omega. And here you see the feasible GLS estimation procedure, how it is done usually when you ask the computer. Okay, so you see that it's an iterated procedure. Right? So suppose you have now we do not just assume that we know omega, but we read this in a way that we say, okay, it's sort of like that one here. No, not exactly. There's no parameters here. Assume that you have a model for omega in a way that you assume that your omega, that you don't know exactly, but you know it depends somehow on a set of variables, right? It depends somehow on income, in our food expenditure example. You don't know exactly how. Well, then you would know omega and everything would be fine. But maybe in your application and in that application it would be plausible to assume that your variance depends somehow on income. How exactly may depend on some parameters, so there's a lot of flexibility here, right? So you assume a parametric model for that drives the heteroscedasticity or autocorrelation or whatever. Okay? So therefore, if you now, we don't assume that we know omega, now we assume we know the general empirical framework that gives us omega. That general empirical framework depends on a finite set of parameters. We don't know. If we would know, then we would know omega, right? But we don't know these omegas, and therefore everything is about estimating the omegas. Now, if we estimate omega, then everything is fine. To be more concrete, look here. Suppose you know that, let's go back to the food expenditure example, where the variance and the information content of the variable depends on the income. So here, BI is now the income of person I. Right? The higher the income, the more uncertainty. Right? So here we just assume it's just proportional to the income. Right? Give me the income, and I'll tell you what the variance is. Now let's a little bit more, more defensive, so to say, right? So from economic perspective, I think it makes a lot of sense to say, well, the higher the income, the higher the variance, but whether it's strictly proportional or not, I don't know. Right? So why not say that the sigma square phi I to the power of gamma, right? So that here to the power of 1. Let's say this is phi e to the power of gamma. So then it's still monotonically increasing. The higher phi e, ei, the higher the variance. But we have a lot of variability to what extent, in what degree, and how it increases. Right? So you might not believe in this assumption. This is maybe too strong, right? Strict proportional, I don't know. Right? But it is somehow increasing, well, and the extent that the data speak, I would say this is a good working assumption, right? So this kind of assumption here is needed in order to estimate, feasible GIS, right? And now generalize this, think, well, the uncertainty doesn't only depend somehow on income, it may also depend somehow on, I don't know, gender or where you live or something like that. Then you have more gammas to estimate, right? And the heteroscedastic, the skedastic function that explains what drives your heteroscedasticity, it can be a multiple regression. Maybe non-linear, I don't know, right? Everything. All right, so this is the starting point now. So, and here you see how it works. It starts with an ordinary square estimation, right? Because, this is a good starting point because we know it's a consistent estimate, right? Not efficient, of course. Yeah, but so far we just have, we don't know what the gamma is. So this gives us a consistent estimate of the actual U has. And now we use the actual U has coming from that inefficient estimation in the first round, right? Could have still some say about the true U's, right? Consistent estimate. Therefore, you can use U hat to estimate the gamma. Right? So, and then with the gamma hat, you can derive the omega of gamma hat, and you can estimate the beta with feasible generalized squared. But of course, this here is based on an inefficient estimation, so there might be room of improvement, right? And therefore, you use the residual of that here and just check how close it is actually to the gamma, to the omega gamma hat, right? And then you re-estimate it and iterate it so long as it's finally converges. Yeah.
And I wanted to ask, how does that actually work? How do we get the new actual gamma hat?
show you in an example. Right? That depends very much on your assumption how omega depends on gamma. Right? In our look here in that example, here when we say, okay, my gamma of my omega of gamma is sigma square the income to the power of gamma, then you are well, then you would estimate then you would take the u squares from your first step regression and regress the u squares on the income. Maybe on log income here, right? Because then the coefficient before that would be okay. Okay. So you see here already, and this is something, right, you should be used to because you're economists, right? That well, if I make, that's always a trade-off between I make an assumption to get something, but then what if the assumption doesn't hold and blah blah blah. So here again, you see, in order, it's critical for the working of this iterative process that the first step works, right? So that the starting point of the process you have is really close, sufficiently close to the true use, because so you need a consistent estimate here. If this assumption does not hold, then bam, it's over. And of course, your assumption about how the omega depend on gamma must be correct, right? So if you here use the wrong functional form, right, which is far away from the true dependence of the true process or factor that drives omega, then of course it also breaks down, right? But if it is a good empirical approximation to say that the variance of your food expenditure income regression somehow monotonically depends on the income level of a person, right? Then you're close enough, right? Okay. So you see, you never know. It's always a model, right? It's a linear model in order to approximate the data generated process or something which I don't know what, right? It's a linear approximation, and that's also an approximation, right? Because of course the variance may depend on income, yeah, that makes sense, but does it really is just the square or proportional? I don't know. Right? It should be close enough to the actual data. Yeah, and here is exactly this here, our proportional heteroscedasticity example, right? And now in matrix form, right? Here again, you see, think of food expenditure and income. Okay? So here the assumption is that the variance, or the conditional variance, of course, because it's random here in the variable case, is, as you can see here, now it's not proportional, it's gamma times x squared. Right? This is just an example, just an assumption, right? And of course you can make it much more general. Right? But here this implies that this omega matrix now looks like this. Right? Here obviously we assume that there is no autocorrelation, right? So there is no, all the off-parent elements are zero, right? So the people are independent of each other somehow. But on the other are the variants of the use, and they are just like this. Gamma times this, gamma times that. And now you see that you have just one parameter estimate. Right? If you have an estimate for gamma hat, then you know, then you have an estimate for omega, and then you can apply GS. Right? And as it says here, if you have something like this is just way to be there. Okay, so you estimate this is ultimately square in the first step. You get some hats. You regress. You take the square because you want to say something about the variance of the use. So you square them and you regress them on x squared, and then the regression coefficient here you get the first round estimate. You see, this is called the stochastic sum. the heteroscedasticity was right. Good news is that this idea to assume a stochastic function, which is plausible in your application, that this idea can be that this stochastic function can take very different forms, right? Here, from here, you have the expected value of t squared, right? So here, the expected value of t squared is just this, right? So the expected value of that is 0, and here, you see, look, this is the this is e, the exponential function. The exponential function applied to a multiple regression, right? And that's of course, why is it, so popular to have stochastic functions like this, with the exponential function, not just this. You have an idea? Suppose we would just let the x pure. And you say, come on, like here, right here you have one variable. Okay? One parameter. Now we can generalize this. Say, oh, come on, maybe food expenditure does not only depend on the income, but the uncertainty in food expenditure. It does not only depend on income, it also depends on gender, age, whatever, right? And we have a lot of sets here. Age, gender, income, whatever you are interested in. And all these, have some parameters that tells you how important that is. Actually, the facts of that. Right? So, what is the advantage of having here this? What might happen is, if you get this, that you're forecasting a variance with negative values. Because if these guys here behave strangely, if you have one person with very low or very high income or high or whatever, right, then it may happen that for most of your observations, this is a very good explanation for u hat squares. But there is someone, but you see what is given estimates, if you increase age sufficiently, if you lower income sufficiently, something, you play around with the sets, then your forecasted variance becomes negative. Okay? And this is something you don't want to have. You don't want to have negative variance. If you take x of it, it's always even then, when the sum of all this becomes negative, doesn't matter. Because exponential of e to the power of minus 2 is still positive. Okay? This is why. Okay, another way to circumvent this negativity problem, right? You see, whenever people estimate covariance matrices, there's a risk that the computer gives you a negative covariance matrix which is not positive definite. In other words, the variances of the diagonal are not positive, but negative or 0 or whatever. Right? So this is a practical problem. Right? So another way to circumvent that, this is one way, is just estimate this stochastic function for the logs. Right? Because the logs of the variances, they can be negative, no problem. Right? Remember how the logarithms look like, right? It's only defined for positive numbers, no problem, because these are positive, right? But of course, they can be negative. Logarithms, if this is below 1, then it's negative, right? But no problem at all, because still the variances are positive. So the variance then would be exponential of that, and that would be positive. Okay, so this is just another strategy in order to circumvent the problem of negative variances. how we can deal with models that have pure heteroscedasticity. So far we just assume away that there is calculation, right? Step by step. So, but of course, if you have your own empirical application, if you run your math, you want to do your math thesis or whatever, you run regression, and now you ask yourself, well, is heteroscedasticity an issue or not? Right? Well, there might be some literature saying, yeah, it is important, so you have to talk about it anyway, right? But if not, right, then you have to think about it. Should I care about it or not? Is ordinary square fine, or should I do GLS or robust errors? So you need a test, right? You need to convince yourself that yes, there is heteroscedasticity, so action required. Or, come on, no, I can't reject now that there's homoscedastic errors. So, fine, ordinary square, standard errors, and so on. Right? Yeah, maybe. Okay. But either or, you have to say something about it. Right? Just applying ordinary square, bam, that's it. Right? That would be not enough. Then your advisor, the reader, the listener of your talk, whatever, doesn't make sense to talk about heteroscedasticity here, for some plausible reason, because literature, because I look at the data and whatever reasons, then you have to say something about it. And the best way to say something about it is to provide results from a test. So how to test for heteroscedasticity? The most popular one is the so-called Gefei-FIONA test. And here is the idea of it. So you see, we start with a skedastic function, right? As here, right? So now we call it just h. It's just a skedastic function. So here we say, you know what? It might be that we have heteroscedasticity, but if we have heteroscedasticity, the starting point of Gefei-FIONA is we have to clue what drives this heteroscedasticity. Because look here, it's not only that we say something about the functional form. You will see this is not so important. But we say, it might be heteroscedastic, but here, this is now a vector. Yeah, we have maybe j regressors, we have maybe j variables. There are j plausible candidates that may drive that heteroscedasticity. So if there is heteroscedasticity in food expenditure income, then income is the driver. Or whatever. Right? You see? But again, it starts with an assumption. We might not know exactly how the functional form is and we don't know the parameters gamma, but we have an idea because we're economists, and this is an economic application. We have an idea what variables are responsible for that. All right. So, and now the trick of the Gefei-FIONA test is we don't work with this h here, which might be a complicated, complex, non-linear function, like the power of gamma or exponential logarithm, I don't know, right? But we work with a linear approximation of it. So, and that's a clever idea because, look, if the null hypothesis is there is no heteroscedasticity, well, that will be always here the null hypothesis, no problem, and then we might reject that there is that and find there is a problem. But under the null, the gamma is 0, and everything, and this is just not important. Under the null. So, and under the null means that actually, we say our reality is, our null hypothesis is homoscedasticity. So we actually, in one point here, gamma 0, and then we look a little bit what would happen if gamma would be not 0. So if we increase gamma a little bit, or we decrease gamma a little bit, so meaning that we are not so interested in, under the null hypothesis, that there is no heteroscedasticity, We're not so interested in the general form of these h functions somewhere for some arbitrary z's and gammas, whatever. No, we're only interested in how does this h function, behave locally close to the value of gamma under the null hypothesis. All right? So h is somehow, but we are interested in how does h behave under the null hypothesis when gamma is 0. And that explains why h, the first derivative here, is a constant, right? Because we evaluate this under the null hypothesis at that point, right? And then h has some, first derivative, okay, but the approximation here, the linear approximation is that we talk about h not globally, but locally, and then we can use the linear approximation. What you see here is just a differential of that function, right? So why does h here change? Well, it might change because delta changes, and then you have a coefficient for delta, and it might change because gamma changed, and then we have here the first derivative with respect to gamma, right? But both are 0 here. So, and now you see, so this is a constant here, and this is a constant because it's evaluated at a certain point, right? And now you see that you have here, you have here nothing but a regression of these heads here, estimated heads in the first round, and then you have a coefficient here and a linear regression there. So this is just constant. Okay, so I guess this is from the Davidson-McKinnon book. So this is here the notation. I don't know whether that's 1-to-1. This is not exactly the same, right? Because we have here still a constant, right? But that doesn't matter, right? The upshot is, and therefore it's okay to use the same parameters, although the notation might be not the same. The point is that you have here so-called auxiliary regression, where you regress the squared u hats you got from the first stage, and now you regress them on all these estimates. So this is a vector, right? This is a vector of, we have these j variables, and this is also a j-dimensional vector, which, for each of the sets you have one b gamma. And now the question, and now you see, well, if the variance of the u's actually depend on the sets, so if there is heteroscedasticity of that form, then that should be non-zero, right? Under the null hypothesis, we have homoscedasticity, so expected value of this is just a constant. This is 0. Under heteroscedasticity, bam, this here depends on the sets. Well, this is non-zero. Okay? So the beauty here of that Boich-Pagan test is that the test here, that you have to make an assumption about the variables that drive the heteroscedasticity. So in order to run this regression, you have to make some assumption what are the sets, right? But that word, that auxiliary regression, looks the same irrespective of what assumption is here relevant here for the h. Right? You see, because h is constant with this trick of linear approximation and the trick of evaluating that under the null hypothesis, you don't have to make assumptions about the stochastic function. It can be like this or like that or like that. It doesn't matter. The test equation, the test regression will always look the same. So that's great, right? So, and of course, as I said, under the null this is 0. If, however, under the alternative, this depends on set, so on the alternative, that should have here explanatory power. So, well, look at that. Of course, you can run an F-test, yeah, on the V gammas, or you can do, you can use this R square statistic, you know, which has an asymptotic chi-square distribution here. So, because again, look, this is R square of that regression, and if this R square is 0, then the sets have no explanatory power for the variation in the U hats. Obviously, sets play no role, obviously homoscedasticity, right? By contrast, if this R square of that regression here is high, or clearly not 0, that would mean that, all right, so there is variation here in my variance in the squared return, squared errors, and I can explain that variation significantly here by the set. Okay? All right. So that's the Gefei-FIONA test, and there is a generalization of that test here of white, the so-called white test, and he showed that you can even include here higher orders term of sets, so you can include here set square and set, or interaction terms of set 1 and set 2 or whatever, right? So there's also, in many statistical programs, the white test is actually a test which runs a regression like this, but only uses variables that are already in your mean equation here, right? So the white test, you know, if you run a regression like this, and then you say, would you please run the white test because I'm not sure whether there is, or I want to show that there is, or I want to make sure that there is no heteroscedasticity. Bam, white test. Then they will run this regression, and the program will run this regression and only include the regressors of S. Right? In the more general Gefei-FIONA test, you are asked, yeah, Gefei-FIONA, yes, why not? Would you tell me what are the sets? And then you type in the sets. Yeah, I think variance could be related to gender, age, income, whatever. Okay. So in a way, you know, this classical white test, where you're not asked to give in more inputs, you know, on the sets, right? But just use the regressors. This is in a way a test in situations where you don't care, or where you have no clue, right? There might be heteroscedasticity, but I have no clue what drives this heteroscedasticity. I have no idea, right? So, yeah, okay, then do the white test. Yeah, but if you have a plan, if you have an idea, yeah, then of course that makes it much more interesting then to apply the Gefei-FIONA test with regressors where you actually have a story about it, right? Like this food income story, right? Where one sees, come on, an economist, he knows the data, he has something to say about it, right? This is much more interesting than just saying, come on, just throw everything in which is in X and just look whether something is explaining the squares, right? Okay? So, we should know that. We don't know H. We don't have to know H. Great. Let us now talk about the second problem, the autocorrelation of the figures. And here I show you simulation results for the most popular model for autocorrelation. This is the auto-regressive model of order 1. And here you see it. Here you see we have a regression model, there are errors. Now we're in the time series context because, as I said, autocorrelation is actually only sense in the time series context. Therefore, we have now T and not I. And here we assume that ut depends on ut minus 1. So obviously, if rho is not rho gives us the correlation between ut and ut minus 1. Okay? Obviously, under the null hypothesis of no order correlation, rho has to be 0. Yeah? Right. So, here are the other assumptions. Rho should be false 1, otherwise the problem the model might explode. We have a degree of Gaussian regressor, so we can estimate that here in the first step consistently. Now look how rho is to be interpreted. Rho is the order correlation coefficient. So it's the covariance between ut and ut minus 1 divided by the variance of ut. So this is the covariance. The covariance, yeah. Look, covariance of ut and ut minus 1 is the covariance of, well, here's just the formula for ut. And now we see, if I multiply that out, we see we have, ut and ut minus 1 have a covariance. The variance of this is sigma square, so if you divide covariance by variance, you get just rho. You can do the same thing for order correlations of higher order. So if you're interested in the covariance between ut and ut minus 2, ut minus 3, ut minus 4, ut minus h, then the algebra is very similar, and you can show that the autocorrelation function of order h, find like this, is just rho to the power of h. So, if your residuals of your regression model follow actually that most popular model, an autoregressive model called 1, then the autocorrelation structure of that here follows a geometrically declining process. Right? So rho, usually in economic applications, rho is positive. Right? So, and then we have a pattern that looks like this. So if rho is, I don't know, 1.8, then rho square is 1.64, and so on and so on. It declines geometrically and converges to 0. Right? So you see here that if you have an autoregressive model of order 1, then obviously ut depends on ut minus 1. But you see that, yeah, well, that's not the whole story, right? You have a dynamic process here, so if this holds, then of course also ut minus 2 has some say on ut. Yeah, because ut minus 2 determines partly ut minus 1, and ut minus 1 determines partly ut. So the dependence is longer than just one period, right? But also, very intuitive, I would say, this dependence, the strength of this dependence gets weaker and weaker and weaker and weaker and weaker. Because there are so many steps in between until finally at ut. And how that dependence goes down is given here by that formula. In that specific example. Here you see, just for comparison, right? The simulation of normally distributed identical variable. That's the standard normally distributed variable. Right? So this is how our residuals hopefully look like. Right? Ideally. So you see we have here 100 observations or something like that. And it's normally independently distributed with x-axis value 0. Yeah, that looks good. An average 0. The variance is 1, and yes, yeah, remember that rule of thumb, 95% of all observations are in the 2 sigma band. 2 sigma is here 2, and yes, all right. If I would show you that figure and ask you, what is your guess about distribution of this, then the normal distributed would be a very plausible answer. Yeah? And also independence somehow, right? Because if it goes up, it goes down, it goes up, because there is no persistence in the data. Obvious persistence. So look here, for example. Here we have exactly these UTs. We take these standard normal independent, but now we simulate an autoregressive model times VT minus 1 and some white noise. And this is the time series that results. And if you compare this, you see that the major difference is the persistence. So, in this series here, if you're below average, you stay below average. And you say, look here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 times in a row, you are below average. If this here would be an independent variable like here, the probability of being 10 times below average, you throw a coin and 10 times in a row you have 10. This may happen, but come on, right? And here you see, it might be that you are several times below or several times in a row below, but not 10 times in a row, come on. Like here and here. This is the persistence which is driven by that parameter. The higher that parameter, the smoother looks the time series that is evolving, because the higher gets the persistence. The longer are the periods where the series is always below or always above average. Yeah. Okay. This process is the basis of time series analysis, and we talk a lot about that next semester in the time series course. You do dynamic macro in your course, in the macroeconomic analysis course. Dynamic macro means lag variables, right? Means time series analysis. Yeah. If you look at shocks, we have DSG models with correlated shocks already. DSG models is not in macroeconomics. Look, if you have dynamic models, then you have some consumption function or IS function or whatever function, and then there is a residual, some shock. And the shock in these G models are typically autocorrelated, persistent. Because you don't have boom, and what's next quarter? Boom, maybe a recession. No, come on, they're not IIT or something. Yeah, you have a boom today, there's a tendency you have a boom tomorrow, right? And vice versa with recessions. So these shocks are autocorrelated. They are positively autocorrelated. And if you look into these models, you often see this bam. This is how shocks are explained or are modeled in macro, right? So the I model is really the workhorse, right? Which you should really understand the dynamics in order to be able to look at those DSG models. Okay, so here we have how to, if we assume that the error here follows in fact this I1 model, then we can estimate variance, covariance. I don't want to talk too much about that because it's just time series analysis. The major point here is that it's relatively easy to show that the covariance matrix omega is now just like this. Right? Look here, we have here this gamma square, gamma here, gamma to the power of h, right? And this here shows up now here in this covariance matrix. If I have n observations, and this is the last thing I can have. All right. So yeah, so you have somehow to estimate the rho, and if you have an estimate of the rho, then you can estimate, then you can write down this omega matrix. Right? And if you do this with to estimate the position, right, this phi matrix looks like this. Right? These are just what you see in old textbooks is that if you have an I1 process in the residuals, it's often suggested to apply the Cochrane-Urquhart estimator. And these are two guys. And the Cochrane-Urquhart estimator does the following. It estimates in the first step the rho, and then it transforms them all like this. Yeah? And you see, look, what is done here is more or less something very similar to GIS. Because we transform, so the starting point is a model like this. Y depends on X, and there's a regressor, and the regressor depends on rho, right? The starting point is always an OLS regression, like in feasible GIS, right? Then you need a model for your heteroscedasticity or autocorrelation. The model is here in I1 process. So you take your U hats, regress it on U hat t minus 1 and get an estimate for rho. And then you might iterate it, yeah, or not. And then you have an estimate for rho, and then you can transform it like this here, the model. And then epsilon ET should be white noise. Okay? So this is the way feasible GLS can be applied if you assume that the error process in I1, and in fact, that can be easily generalized to higher order recursive processes, so that's not an issue. But let us now talk about, well, in parallel to our strategy when we dealt with heteroscedasticity, now what's going on, how to test for the relation, right? And of course, tests from a lot of tests from the bachelor course, but let me say that this is here one you should use. The Preuß-Gottfried test. And if you look at it, it works very similar as the Preuß-Pagan test, and in fact, it's also a Lagrange multiplier test. So it is based on auxiliary regression. Okay, look here, the starting point. Explain for the empirical relevant example of an autoregressive model here in the videos. So, look here. If yt is this and ut is that, then you can show that, well, ut is nothing but this here. Yeah? Look here. Ut is, because ut minus 1 is xt minus 1 beta. If you plug that in, you see that that holds. Okay? So here is yt, xt, beta, and now we replaced ut with rho times ut minus 1 plus epsilon, and ut is nothing but yt minus 1 minus xt and so on. Okay, this is that's trivial. Okay? So, and now let's look at this here. And you see, under the null hypothesis here, so this here is some x some regressor here that somehow depends non-linearly on beta and rho. Okay? So, under the null hypothesis, rho is 0. Under the null hypothesis, there's no relation, and this is what we want to test. Yeah. If rho is 0, then you see that that you can use this auxiliary regression, the UTs, again, the first step is always run the OS regression to your model and take the UT hats, right? For the Preuß-Pagan, where we were interested in the variances, we took the UT squares. Now we are interested in autocorrelation of the UT, therefore we take the UTs. And we regress them on the ut minus 1, right? Which is here, ut minus 1. And that's important to note, also on the regressors here of the model, because it's also here, right? So we do not simply run the regression ut on that, we also control for this. And this is a direct consequence from that. Okay, and again, of course, the extension higher order model is here super simple, because it just means that you have here ut minus 2, ut minus 3, and so on and so on and so on. So if you're not interested in null hypothesis, there is no autocorrelation of order 1. You can also generalize that to there is an autocorrelation of order 12, or whatever is interesting in your application. Then you run this here with ut over 12. So, and then the idea is exactly the same as the Preuß-Pagan test. You can now, if you run this regression here, these are consistent estimates here of the null hypothesis. So you run F and t-test or whatever right here. The t-test would be okay. You can also run an F-test if you have higher order piece. And then the null hypothesis that ask that all these coefficients are 0, or that the NR squared statistic is 0, whatever is implemented in your statistical program. Okay, so this is a test time series econometricians apply. Okay, and here are the tests you know also from bachelor. Young box test, the so-called Q statistic. You know that? So this is a statistic which is typically shown when you ask the program, would you please give me the autocorrelation function? So something like this, right? Would you please estimate the autocorrelation function? Then usually there are confidence bands here, whether it's 0 or not. And there is a Q statistic for various flags, where the null hypothesis is all these bars are actually 0. Right? So this is the Q statistic, or the New box statistic. So it's sum up here all the estimated covariances, right? And look, this is just here. This looks complicated because it's a small sample adjustment, right? The traditional Q statistic or box peer statistics was just here, that one here, and that shows it's just summing up the squared estimated order covariances. Yeah, well, and under the null it's 0, so you don't want to have here large numbers, and you can show that these are chi-square distributed and so on. The problem of this new box statistic is, however, that it requires strong assumption about the regressors, right? So it works only if it's exogenous. So if you have something with like endogenous variable, it becomes problematic. It assumes homoscedastic errors, yeah, because if you estimate here the autocorrelation, right, you have to make some assumption about the variances, right? So if that does not hold, then the box peer statistics become problematic. So it is a nice statistics to get a first impression on whether there are significant autocorrelations or not, but don't base your math thesis on the statistic. You will be criticized for that, right? Same thing, and even more severe. The Derwin-Watson statistic. You all know the Derwin-Watson statistic, do you? Mm-hmm. So in most statistics, did you apply a statistical software program in your econometrics bachelor? Which one? R. Nice, we also do it, right? Because you're going to be pro, right? So you should know what you're doing. And if you know what you do, R is perfect. If you don't know what you do, like bachelor students, problematic. Because, because it does not offer you things, right? If you have programs like data or EDUs or so, if you run a regression, then there's a standard output showing you everything, right? And then you see things and you start to think about these things, right? What is the relation between them? Then there are a lot of relations between statistics, right? And then you learn a lot. In R, I don't know whether you learn a lot in R. For simulation, perfect. Yeah. For our purpose, you're going to be now a researcher, doing your own data project, then come on, yeah, R it's good that you know R. You know how to use R. But, so, Derwin-Watson is one of those statistics which are traditionally offered by standard regression outputs. And here is the Derwin-Watson statistic. Ta-da! So, the Derwin-Watson statistic, one of those, there are a lot of reasons why Derwin-Watson statistic is actually not a good statistic. The first one is that it only tests for first order calculation. So if you look at the formula of the Derwin-Watson statistics, then you see that it's in effect asymptotically it's just 2 minus 2 times rho 1 hat. So on the null hypothesis of rho 1, 0, it should be close to 2. Right? And you see in the empirical relevant case of positive autocorrelation, you see that this goes to 0. Right? So German one statistic always between 0 and 4 by construction. 4 means strange negative order correlation, and if it goes to 0, this is a strong indication that there's something going wrong with first order correlation. Right? So first order correlation is a classic case, right? So you can construct examples where there is no first order correlation, second, third, fourth, fifth order, right? But these are constructed. This is not what should happen. Right? So if the German one statistic says, oh, I'm close to 0, then there is order correlation problem. Right? The question is now how close is close. And here comes the second problem. There are no nice critical values. Right? Gefei-FIONA, yeah, asymptotically TBS and chi-square, great. For German Watson, there are no critical values. They depend actually on your regressors and your model, and there are only upper bounds and lower bounds for critical value. It's a mess, right? And if you look at your data or EUs or whatever output, then you see no p-values for the German Watson statistic, and for a reason. There are no p-values. Okay? So forget German Watson. Oh no, don't forget it. Yeah, you should know it. Yeah. Because it's so famous statistic, right? Every academician knows the Watson statistic, but you shouldn't use it. Yeah. So, same for Q statistic. Well, it's shown so often, right? Even in modern empirical papers, and it's a nice informative statistic because it's so easy to interpret, right? If you tell me Q is I don't know what, right? I know Q is the sum of the squared autocovariances, right? I have a feeling on the size, right? But here these statistics here, F and t-test or n square or absolute regression, they have better statistical properties, but they're not nicely to interpret. Yeah. Okay, so this old school don't use. That's also not very recent, but statistically the best. And one of the major differences is here that you include here the regressors, right? Which I forgot is in here, right? When you just regress on these. Okay, cool. 3 minutes left. Come on. Summary. Looks good. Let's go. Let's go. So that was the first strategy. Well, we have GNS. If we have an idea about the omega, then we can transform the model. Everything is fine. We talked about tests. So is there actually order correlation or heteroscedasticity? And now we talk about the case. Well, what if not? Well, we have no idea about omega, right? So here is. So what can we do in order to still get some standard errors, which are somehow robust against heteroscedasticity and order correlation? So this is the formula we already derived, right? This is the variance. If you would know omega, then the true covariance matrix giving us the correct standard errors, t-test and f-test and everything, which look like that. But this is what we don't know. The key idea here of finding robust standard errors is, look, omega. What is the dimension of omega? N by n. N, we have 1,000 observation, it's 1,000 times 1,000 matrix. Oh my god, right? This has really a lot of coefficients to estimate, right? We can't do that. So we cannot do an estimate of omega in a general case. No way, right? But the idea is, look, what we need for this matrix is actually not an estimate of omega. We need an estimate of x prime omega x. And the dimension of that matrix is k by k. K by k. K by k is small. K, you have 3, 4 regressors, it's a 4 times 4 matrix. So wow. Okay, this is the brilliant idea of robust standard errors. We call this here this is often called a sandwich estimator, right? That's important to know, but right, you see here, we have something here, the outside, which is identical, right? And then we have a filling, and this is the interesting thing here, sandwich. And this, if you multiply it out, it looks like this. Yeah? So these are the entries of the unknown omega matrix, and here we have our regressors. Okay? And now one can show that with that trick, actually we don't need to estimate a 1000 times 1000 matrix, we have to estimate a 4 times 4 matrix, the case 4, right? With that trick, one can show that there are two variants of estimating in this way the robust standard errors. The first one here, the older one, is again White, the one with the test. Yeah? White showed that you can actually use the UI squares from the first step of your regression, so the naive ones, which are however consistently estimated, and just plug them in for the omegas. So this here, he showed that this here is actually a consistent estimate for the filling of the sandwich. Okay? So in the first step, this sounds really weird, right? Look, you have, again, right? You use n estimates, here you use n observations, n estimates of your errors, the square one, in order to have an n times n matrix. Wow, it works. But this, of course, only works in the case of heteroscedasticity only. You see there are no covariances here. So if you know that in your application, because you're running set data or cross-section or whatever, and there's no time component and autocorrelation makes no sense at all, so you might say, okay, there might be heteroscedasticity, and I want to account for that. Then you might use the white standard error, and this is how they construct. They are often called heteroscedasticity consistent standard errors. And if you want to be more specific than just saying robust standard errors, robust can be robust for outliers. Right? So, these are the white ones. It took 7 years or so for two statisticians, Yu and West, to generalize this idea of using a sandwich estimator here for the variance to generalize this to the case for general omega, so where you have not only heteroscedasticity, but also on the off layer correlation. Right? It is a little bit, so the general idea is the same. So your estimate is based on the UI hat and the UJ hats from the first period. But what is different is now that you cannot just naively plug in here these numbers in this very general formula, because one can show that this then is always 0. Right? So that's not a good idea. You have to manipulate these estimates a little bit. And the way it's done is that you have to weight these errors, these covariances. This is, in a way, an estimate of the covariance between UI, and UJ. And you see here, these estimates here are weighted, W for weight, and that weight only depends on how far away is I from J. Well, in the time domain. And the idea is that, well, the farther this is away, right, here, the smaller the weight. This new West, or sometimes called half standard errors, because they're heteroscedasticity and autocorrelation consistent errors. The general approach here is a non-parametric estimation. Did we already discuss non-parametric estimation? Did you know what a kernel and a bandwidth is? So look here. The idea of these weights is, first, you have something like a kernel function. That's a very general concept in non-parametric estimation. A kernel function means, we talked about non-parametric estimation. A about this unknown function in form f and how to estimate it locally. Come on, right? This is again the idea here. So the kernel tells you which, you have a very complicated function. Yeah, you're a very complicated function, but you actually want to estimate it, and you want to estimate it, and you have some data here. Yeah, and you say, well, if I want to estimate this here, then I don't, these points may have some say about that, but obviously those here are more, those which are very close to it are much more informative and important than that one, which are far away. So, and this is the kernel function. The kernel function tells you how do you treat with, so what's close for you, right? And here are the classic kernel functions here. It tells you, well, look, the way, if this is here true, if this number here, and I would say h is now the difference j minus a. So if this goes too large, then put the weight to 0. Yeah. So if this is too far away, ignore it. Yeah. That's the kernel function. And how far away means away tells you here the b, and the b is the bandwidth. So these are the two buzzwords in non-parametric estimation. What the kernel function, what the bandwidth. And actually, I'm not a non-parametric guy, but what I've heard is the bandwidth, choice of bandwidth, that's a very good choice. How do you weigh inside the kernel? Of course, it has in small samples some, but this is important. So there are rules out there how to choose the bandwidth. Okay? Here's the Bartlett kernel. Right. But that's the Bartlett kernel. Okay, so this is how these empirical estimates of covariance have to be weighted in order to get a consistent estimate for the standard errors. So this is done when you see a table when you read an empirical paper, and in the footnotes, the table is we use robust standard errors, or we use new wet standard errors, or we use hack standard errors, and they don't care about, or they don't know what is the source of the autocorrelation and the error specifically, but there seems to be one, so we want to be on the safe side and use robust standard errors. Okay, so this is the summary. So suppose you have your test indicate that regression yields heteroscedastic and or autocorrelated, right? So it looks like this one here. Omega is not just sigma squared times delta. So if you know the function form of omega, so if you have really an idea what drives the autocorrelation, your autoregressive model, auto 1, 2, 3, 4, right? Or elasticity I depends, you have the idea of the elastic function, then go with feasible GIS. It's the efficient way to do it, right? But of course, it depends on whether your assumptions are correct. Right? So if you don't know a function form, or if you don't care about it, right? Most cases they just don't care about it. Use robust standard errors, hard standard errors. Yeah. And if you are sure that autocorrelation makes no sense in your application, use blind errors. Not accidents. Okay, here an important note. In econometrics in the bachelor, and also here so far, right? Autocorrelation of residuals is always seen as something, something doesn't work. It's a problem. We have to account for it. Errors are wrong. It's just, we would be much more happy without that, right? This is, however, a very misleading view of autocorrelation, because think about the macro models, right? Where would all these dynamic macro models be without autocorrelated residuals? They're just not dynamic anymore, right? So you need, because data is persistent out there, right? You need autocorrelation in order to explain this, right? And therefore, and this is a starting point of dynamic models and time series analysis, if you want to forecast, and there is no other relation to data, you cannot forecast. Because forecasting means I have information today, I can use this for tomorrow, right? Or the correlation. Today has a say on tomorrow, and yesterday has a say for today. That is the dynamic model, and this means there is autocorrelation, right? So if you're doing forecasting, you want to do dynamic models, if you're interested in time series analysis, if there's no autocorrelation, you're disappointed, right? Because there's no way to forecast. There's no information in the past for the future. So what can I do, right? So therefore, if a guy like me sees autocorrelation, he's trying to model this autocorrelation, to account for that autocorrelation. For example, look here. Look here. You know, if you run such a model, a static model, without dynamics, without lag and Hodges variable, no proof, and you find something like that, I wouldn't apply hack standard errors or something. I would try to estimate a dynamic model like this, where I really see, yt depends on yt minus 1, how interesting is that? And maybe lag x also play a role. And then I can talk about dynamic multipliers and impulse response functions and all these, all the blah. Then I understand the dynamic of the models. And this is much more interesting in many applications than just say, I know it's not a static model, there is autocorrelation, but come on, here's a bomb, the hack standard error, and then I just say it's all right. I don't care about dynamic. I don't want to understand the dynamics, I just want to have robust standard errors. Right? So there's a nice paper, of course, from a time series implementation, and in the Journal of Econometric or so, it has important news for autocorrelation correctors. Don't. So, because you really don't like it. But in practice, it might be a good idea. Okay, so that was it. Thank you very much for coming today. 5, 8, 9, 10, 13 people will do the final exam. I hope you have a nice business break. Yeah, we will see already in the second week of January. Monday morning after Christmas, math, first semester. So that would be that's a challenge. But not fun. Right? Yeah, and then we will talk about this with a very important topic. Thank you for coming.